You think you know what big means. You don't. Not yet. And by the time this video is over, the word is going to mean something completely different to you. Here's the game. We're going to start with something you can actually picture, your own body, standing on a rock orbiting a fireball in a corner of space so vast that even light, the fastest thing that exists, would need longer than every human who has ever lived to cross just the part we can see. Let's start zooming. Stand next to Mount Everest and you feel small. That's the correct reaction. At 8,849 meters, Everest is roughly 5,000 times taller than an average human being. Stand at its base and look up, and your brain genuinely struggles to process the scale. Now here's the first zoom-out moment, and it's going to happen a lot. Everest, the tallest thing on the surface of our entire planet, the mountain that has killed climbers who spent their whole lives training to survive it, is barely a scratch on Earth's surface. If you shrank the Earth down to the size of a basketball, Everest wouldn't even be as tall as a coat of paint. Earth is 12,742 kilometers across. Everest is a rounding error. And here's a strange twist before we even leave Earth. Everest isn't even the tallest mountain in our own solar system. That title belongs to Olympus Mons on Mars, a volcano roughly 3 times taller than Everest and wide at its base that if you stood on its summit, the ground would curve away from you fast enough that you'd never see the edge of it. We're not even off our home planet yet, and something bigger has already appeared. That's the pattern for the rest of this video. Get used to it. So forget the mountain. Let's zoom out to the whole planet instead. Earth feels massive when you're standing on it. It takes a commercial jet about 2 full days of non-stop flying to circle it once, roughly 40,000 kilometers, the entire circumference of the planet. And yet, if you could hold the Earth in one hand and the Moon in the other, you'd notice something strange. Every other planet, moon, and rock you could fit between the Earth and the Moon, all of them side by side, would just barely fit in that gap. The average Earth-Moon distance is 384,000 kilometers. Light, again, the fastest thing that exists, crosses that gap in about a second and a third. That number, a second and a third, is going to matter in a moment. Hold on to it, because we're about to leave Earth completely, and the units we're using are about to become useless.
Forget kilometers. From here on, thinking in kilometers is like trying to measure the distance between countries in inches. Completely possible, completely impractical. So we're switching units to the same unit astronomers use, the time light takes to travel. Light takes about 1 1/3 seconds to reach us from the Moon. It takes about 8 minutes and 20 seconds to reach us from the Sun. Every time you watch a sunrise, you're watching light that left the Sun's surface roughly 8 minutes earlier. The Sun could theoretically vanish right now, mid-video, and you wouldn't know for 8 more minutes. And the Sun itself, the object so bright you're not supposed to look directly at it, the object responsible for basically all life on Earth, is so large that you could fit about 1,300,000 Earths inside it. One star, a million Earths. Now zoom out again, because the Sun is just the beginning of the solar system, not the whole thing. Past Earth sits Mars, then the asteroid belt, millions of rocky fragments left over from the solar system's formation, spread across a gap so wide that spacecraft routinely pass through it without hitting anything at all, despite what movies show you. Past that sits Jupiter, a planet so large that roughly 1,300 Earths could fit inside it, with a storm, the Great Red Spot, that has been raging for at least a few hundred years and is itself wider than our entire planet. Past Jupiter, Saturn, wrapped in rings made of ice and rock that span up to 280,000 kilometers across, while being, in places, only about 10 meters thick, proportionately thinner than a sheet of paper laid across a football field. Neptune, the outermost official planet, sits so far away that sunlight takes about 4 hours to reach it. 4 hours is the time a radio signal from Earth to a spacecraft near Neptune takes one way, which is exactly the kind of delay engineers actually have to plan around when flying probes that far out. Just past Neptune begins the Kuiper belt, a second, icier debris ring that includes Pluto, reclassified in 2006, but still one of the largest known objects out there. But even the Kuiper belt isn't the edge. Humanity has actually sent something farther than any planet. Voyager 1, launched in 1977, is now so far from the Sun that sunlight takes over 22 hours to reach it. 22 hours. That's an object built by humans still transmitting data back to Earth after nearly 50 years, and it still hasn't left the outer edge of our own solar system's territory. Because past Voyager 1 lies the Oort cloud, a vast, thin shell of icy debris surrounding our entire solar system, extending out to roughly a light-year and a half from the Sun in every direction. That shell is considered the true boundary of our solar system, and it's so large, so sparse, and so far away that if you shrank the distance from the Sun to Neptune down to the width of a coin, the outer edge of the Oort cloud would still be more than a kilometer away. That's our solar system, genuinely one of the largest single structures the human mind can partially grasp. It is also, in the story of the actual universe, essentially nothing.
Here's where the numbers start to break. The nearest star to our Sun, not a planet, an entire other star, is Proxima Centauri, roughly 4.24 light-years away. That means light, moving at 300,000 kilometers every single second, takes over 4 years just to cross the gap to our closest stellar neighbor. Voyager 1, humanity's fastest and farthest spacecraft, has been traveling for nearly 50 years and has covered a distance that light crosses in about 22 hours. At that rate, Voyager 1 would need over 70,000 years just to reach Proxima Centauri, and it isn't even aimed at it. Now zoom out from a single star to all of them. Our Sun is just one of somewhere between 100 and 400 billion stars in the Milky Way. Astronomers genuinely aren't sure of the exact number because we're inside the galaxy trying to count it, like trying to count every tree in a forest standing in the middle of it. The Milky Way itself is roughly 100,000 light-years across. If you shrank the entire Milky Way down to the size of North America, our solar system, the Sun, every planet, the Oort cloud, all of it, would be smaller than a single grain of sand. Our galaxy isn't a uniform blob of stars. It's a flattened spiral, with curved arms of denser star formation winding out from a central bulge, the way water spirals when it drains. We live inside one of those arms, a relatively minor one, nicknamed the Orion Arm, roughly 2/3 of the way out from the center, in what astronomers sometimes call the galactic suburbs. Toward the crowded central bulge, some regions pack thousands of times more stars into the same volume of space than we experience out here, and in tightly bound clusters called globular clusters, which orbit the galaxy like satellites, stars can be so close together that a hypothetical night sky there would never truly go dark. and near the center of all of it, behind thick clouds of dust, in a region no visible light telescope has ever fully seen through, sits something our galaxy's roughly 200 to 400 billion stars are all slowly orbiting, a supermassive black hole called Sagittarius A star, 4 million times the mass of our Sun. We went deep into how astronomers proved it was there and the actual 2022 image of its shadow in our last video. It's linked right here, and it's a genuinely good follow-up to watch after this one, since everything you're about to see is technically orbiting the object we covered in that video. That's the Milky Way, one galaxy. Hundreds of billions of stars, anchored to a black hole none of us can see directly, spinning slowly enough that our Sun takes about 230 million years to complete a single orbit around the galactic center, meaning the last time our solar system was in its current position, dinosaurs hadn't evolved yet. And the Milky Way is not alone.
2.5 million light-years away sits Andromeda, our nearest large galactic neighbor, itself home to roughly 1 trillion stars, more than double our own galaxy's count. It's approaching us right now at about 110 kilometers every second, and in roughly 4 to 4.5 billion years, Andromeda in the Milky Way will begin merging into a single galaxy. Neither will be destroyed, exactly. It'll be more like 2 slow-motion rivers of stars gradually folding into one another over hundreds of millions of years. If you're picturing a violent collision, that's the wrong image. Individual stars are so far apart, even within a packed galaxy, that almost none of them will actually crash into one another. Zoom out again, because Andromeda and the Milky Way are just 2 members of something bigger, the Local Group, a gathering of more than 80 galaxies of various sizes, spread across roughly 10 million light-years. Zoom out again, and the Local Group turns out to be just one small piece of the Virgo Supercluster, a structure roughly 110 million light-years across, containing over 1,000 galaxies, with our entire Local Group sitting out near its edge. And the Virgo Supercluster, the thing that contains our supercluster of galaxies, which contains our Local Group, which contains our Milky Way, which contains our solar system, which contains our entire Earth, is itself just one lobe of something discovered only in 2014, Laniakea, a supercluster of superclusters, spanning roughly 520 million light-years and containing the mass of about 100,000 galaxies, all of them flowing slowly along cosmic currents toward a gravitational anomaly astronomers call the Great Attractor. Zoom out past even that, and structures like Laniakea stop looking like isolated islands and start looking like threads, part of something called the cosmic web, an almost unimaginably vast lattice of galaxy filaments and sheets wrapped around enormous, mostly empty voids, hundreds of millions of light-years wide. On the largest scales that astronomers can map, the universe doesn't look like a random scattering of galaxies. It looks like a structure, something closer to a cosmic spiderweb, or the foam on top of a wave, frozen in place across billions of light-years. Some of these filaments are so large they strain the definition of the word object. The largest confirmed galactic structures astronomers have mapped stretch for several billion light-years, arrangements of galaxies so vast that light itself would need well over 1/10 of the current age of the universe just to cross from one end to the other. And in between these filaments sit voids, regions so empty of galaxies that some stretch for hundreds of millions of light-years with almost nothing in them at all. If our entire Local Group happened to sit in the middle of one of the larger known voids instead of near a filament,
we might never have realized the rest of the universe was so densely populated with galaxies, simply because none of that light would have had anything nearby to bounce off of before reaching us.
So how far does it actually go? Here's where this stops being simply large and starts being genuinely strange. The universe is about 13.8 billion years old. Naively, you might expect that means we can see at most 13.8 billion light-years in any direction, since light has only had 13.8 billion years to travel. But the actual radius of the observable universe is roughly 46.5 billion light-years, not 13.8 billion, 46.5 billion, making the full diameter of everything we can possibly observe roughly 93 billion light-years across. That number sounds like a contradiction. It isn't. It's one of the strangest, best confirmed facts in modern cosmology. The universe itself has been expanding this entire time, stretching the space between us and that ancient light while it was still traveling toward us. A galaxy whose light left it 13.8 billion years ago isn't 13.8 billion light-years away anymore. The space between us and it has been stretching the whole time, and by now, that galaxy is roughly 46.5 billion light-years away, even though its light has only just reached us. And that 93 billion light-year sphere is only the observable universe, the portion light had time to reach us since the universe began. It is very likely not the edge of the universe itself. Most cosmologists think the actual universe extends well beyond what we can ever observe, possibly by an enormous factor, and some current models seriously consider the possibility that it has no edge at all, that it's infinite, stretching on with no boundary in any direction, forever. Part of why cosmologists suspect this traces back to the earliest fraction of a second after the universe began, during a period called inflation, when leading theories suggest space itself expanded at a staggering, faster-than-light rate for an almost immeasurably brief moment, stretching whatever region existed at the time to a size far larger than anything light could ever fully cross afterward. If that theory is correct, the observable universe, the 93 billion light-year sphere we can actually see, would just be our own tiny local patch of something vastly larger, the same way a single wave is a tiny patch of an entire ocean you can't see the edges of from where you're standing in the water. Some physicists take this even further, speculating about whether regions of space too distant for their light to ever reach us might have developed under different physical conditions entirely, sometimes loosely described as other universes within one much larger whole. This idea remains genuinely speculative and unconfirmed, sitting at the edge of testable science rather than settled fact, but it's a serious enough possibility that it's studied at some of the most respected physics institutions in the world. We are not talking about the edge of the universe in this video, because as far as anyone can currently tell, there may not be one to reach.
So let's zoom back in, all the way back to where we started. Back through the cosmic web, back through Laniakea, back through the Virgo Supercluster, back through the local group, past Andromeda, into the Milky Way, past Sagittarius A star, out through 100 billion other stars, to one ordinary yellow star, to a small blue and green planet orbiting it, to a single mountain on that planet's surface, to you, standing at the bottom of that mountain, feeling small. You were right to feel small, but not for the reason you probably thought. Every scale we just walked through, your body, this planet, this solar system, this galaxy, this supercluster, this observable universe, is nested inside the next one, like the world's most extreme set of Russian dolls, except every single doll turned out to be bigger, stranger, and older than anyone standing at the smallest scale could have possibly guessed. And here's the part worth sitting with. You're not just small compared to all of that. You're something rarer. You're a temporary arrangement of atoms on a small planet in one arm of one galaxy that has somehow become organized enough to look outward and actually work out how big all of this is. Atoms understanding the universe that made them. Maybe that's the actual takeaway. Not how small you are, how strange it is that anything small enough to stand on a mountain ever learned to measure the distance to the edge of what it can see. If your brain is still a little bit broken from that jump in scale, good, that's the correct response. Subscribe and turn on notifications because this channel exists to keep doing exactly that to you, one real, evidence-based deep dive at a time. If you haven't already, go watch our video on Sagittarius A star, the black hole sitting at the center of everything you just saw get zoomed past. It's linked right there, and it picks up exactly where this one leaves off. One question before you go. Out of every scale in this video, your body, Earth, the solar system, the Milky Way, Laniakea, or the observable universe itself, which one broke your brain the hardest? Put it in the comments. We read every single one, and it genuinely shapes what we cover next. Thanks for watching. We'll see you in the next one.